Your first task for today is to count some M&Ms. So what we're going to do today is test some things about the distribution of all of the colors of M&Ms. Up until this point, we've talked about the proportion of a single outcome, just a success. So in the past, we may have had to test just the proportion of M&Ms that are red, or just the proportion of M&Ms that are blue, for example. Today, we're going to show a way to test the proportion of M&Ms that are all of the colors. So don't worry if you don't have any M&Ms at hand. We're going to have an example data set here in a minute. However, if you want an excuse to need a few M&Ms and count along, that would be just fine too. So what we want to ask are the colors evenly distributed? That is, are there the same number of reds and blues and yellows and browns in a pack of M&Ms? Now, we wouldn't necessarily expect that in any given pack of M&Ms or glass of M&Ms or however many M&Ms you're eating, we're going to get exactly the same number of each. So we want to know, is that difference significant? That is, do you think that the population is not also evenly distributed? So do you think that your observed data are enough to conclude that it's unlikely that the rest of the population is evenly distributed? How do you think we can test this? So today we're going to walk through the steps. First I'll show you by hand, and then in a separate video I'll show you a series of examples of different ways to do this with the computer. So the first question we have to ask is, how different are our observed values from what we would expect by chance? So we would first need to consider what our null distribution would be. So in this case, our null distribution is that there are the same number of M&Ms in each color. So we don't necessarily expect exactly that value, but we expect that over the long run, we'd get about the same number of each. For each color, we would expect a certain number. That is, if we count up your data, so here I have a combined set, so this is actual data from one of the students in the in-class version. We can count up here and we see that we have 54 M&Ms of these various colors. Now, we would expect, if 1 in 6 is each of these 6 colors, that if we take our 54 times 1 in 6, we would get 9 of each color. So the question we want to ask is, given that we expect 9 of each color in our bag, how different is what we've observed from the actual even distribution? So we want to maybe first ask, how far off are we with each color? So if I observe 14 blue M&Ms in a pack, we would take 14 minus 9 and get 5. So we might want to first try adding up all of the values. Note that it's always observed minus expected. So we can add up those differences as a way to combine them. So we take 5 plus 0 plus negative 4. So negative 4 is because we have 4 fewer than are expected. Okay. Positive 1 because we have 1 more. Negative 2 because we have 2 less. And 0 again because we have that same number. However, if we add these all up, we take 5 plus 1, we get 6. Negative 2 plus negative 4, we get negative 6. We get a total of 0. This will always be true. Every time you count up M&Ms and these types of things, you will always get a sum of 0 as your difference from your expected. Now this is important. It means we need a slight tweak to our approach. So in the past, how did we deal with adding negative numbers to positive numbers? So you might recall that for our calculation of the standard deviation, we squared each of our deviations in order to get a positive number for each. So we can do that same thing here. So we square then add, so we take 5 squared plus 0 squared, the square doesn't matter here, plus negative 4 squared plus 1 squared plus negative 2 squared plus 0 squared. We can add that all, or multiply those out, 25 plus 0 plus 16 plus 1 plus 4 plus 0. Okay, we can add those all up and get a value. However, the difference of 3 counts matters more when the expected is 6 than when it is 66. That is, if we expect to get 6 M&Ms of a given color and we only get 3, we're missing half of our M&Ms. However, when our expected is 666, that 3 counts is going to be a very small difference. So the way we handle that is by dividing by our expected counts. So essentially what we're asking is, what fraction off are we? So we standardize and then add. So we take each of those values and divide by 9, because recall from the previous slide, that was our expected count. We get 5.11111, so 5 and 1/9. This is called the chi-square statistic. So this statistic tells us how different our observed values are from our null expectation. This can be formally written out as the sum of observed minus expected squared divided by the expected. So that's all we did up here. We took our observed, so on the previous slide, observed minus expected to get this value. We squared them to get this value, and then divided by our expected. But now we want to know is this value big? That is, does 5.1 mean that we should consider rejecting our null hypothesis? For that, we're going to need a new distribution. So the distributions we've used already all have negative values. But as you noticed, when we're adding those numbers up, because we're squaring, they always have to give a positive value. So we need a new distribution. This distribution is called the chi-square distribution. So in StatCrunch, we can go stat, calculators, chi-square. I'm going to do that here. So stat, calculators, chi-square. We can see that we can get a range of degrees of freedom. Now these degrees of freedom are one less than the number of categories. So when we have 5 categories, we expect to see this particular shape. Now you'll note that as the degrees of freedom go up, so here if I put in 20, the shape changes. Okay? And as we go larger and larger, let's say 1,000, it starts to look a lot like the normal distribution. However, always notice that the mean, so the center of the distribution, is always at the number of degrees of freedom. That is, we expect our counts to be more different when we have more bins to put things inside of. So we want to enter in 5, because we have 5 degrees of freedom when we have 6 categories. We want the probability of being greater than 5.111111. So if we click compute, note that it shows this red up in the positive part of the tail. Because the chi-square statistic is always, by definition, positive, this is the only direction that we can be extreme in. So here we see that 40% of the time that we collected this many samples, we would expect to get a value this extreme or more extreme. So those degrees of freedom I mentioned are one less than the number of groups. And you can see here I've superimposed the degrees of freedom from 2 all the way up to 10 on top of each other, so you can see how the shape of the chi-square distribution changes as we move along. This allows us to calculate a p-value, which is what we did when we went over to StatCrunch.